me show you how to be a good breezy and change your predictions.
Hello, my dear Bayesians! And today, before the BITESIZE, I wanted to share with you that Max Gabriel, of course, an LBS alumni and, well, now kind of a colleague and friend of mine, well, he single-handedly thought that it would be a good idea to transfer some part of our Soccer Factor model onto its own dedicated website, and he was really right. He did that with great mastery, so I definitely encourage you to check it out. Just a recap about what this is. This is a model that Max and I worked on last year, inspired by the financial literature on asset pricing and performance attribution. It's a Bayesian regression model for soccer player skill evaluation, and by its current design, the model predicts football or soccer player's probability of scoring a certain number of goals in his team's upcoming match. And so on the website, Max put everything. What you'll find is real-time and historical scoring probabilities for hundreds of strikers in Europe's top leagues, and upon popular request, so upon my request, because I am a pain to work with, Max was so kind to also add Ligue 1, so the French league, to the stack of originally covered leagues. So in there you'll get the Premier League, Bundesliga, Serie A, La Liga, and now Ligue 1. And we update the website weekly. We run the model every week. So that's the cool thing. Like, we came up with a model, and that's not only development, but we also have a production workflow now that runs the model automatically every week, every Tuesday after the games of the weekend. And that's throughout the regular football season, with the latest predictions for each league's upcoming match day. So this is I thought, a very cool use case of an idea that originated in a paper, and now that is run every Tuesday, every week after games, and now that you can see on a dashboard with a lot of plots that come from Bayesian models. So if you work with them, you will be very familiar with those plots. In the future, the project is ongoing work in progress, so we will probably add additional features and eventually models. And we're very grateful for any type of suggestions you may have, requests, inquiries. Feel free to reach out directly to me or to Max. If you want to work with us on this project, please reach out. If you want to get some direct modeling experience in sports with myself and with Max, please do reach out to us. I will put the links in the show notes for the BITESIZE, the LBS episode where Max came on the show and talked about his original model, the archive link where the paper is, and of course, the link to the dashboard. That was a long intro, so now I'm gonna let you enjoy the BITESIZE with Gabriel, who is a much better speaker than myself. Thanks for hearing me out, folks, and best Bayesian wishes to you all. Yeah, something I really want to talk to you about, because that's something you've worked on for a long time. Like, this was really a masterpiece. So thank you first for doing that. And this is your re-implementation of BART, Bayesian Additive Regression Trees, in Rust. So people probably know you can do BART models with PyMC in a sub-package that's called PyMC BART. And this is an awesome package. I use it whenever I can, but it has the defaults of regression trees, which is, you have, if I remember correctly, you have as many parameters as you have rows in your dataset. So that means it grows pretty fast in the computational demands. So yeah, in my experience, when you start passing 200K observations, it starts to be really slow to infer. So what you did is re-implement the sampling algorithms, which is Metropolis Gibbs, I think, or something like that. What algorithm is that?
Like a particle Gibbs.
Yes,
stuff.
that's particle
Yep.
Gibbs. Yeah. So particle Gibbs, and you re-implemented that in Rust. So yeah, can you talk about that? Like, basically, why would you start doing that? And basically give us the elevator pitch for the project before we dive a bit deeper.
Yeah, so the PyMC BART project, this really kind of, I believe, comes from Osvaldo. And about a year ago, he reached out. He's like, "Hey, we need to make this thing faster. Are you interested?" I'm like, "Hey, I'm all for it. Let's do it." But before that, I really hadn't used BART or was too familiar with the method. I mean, I was familiar with more like gradient boosting techniques, which is somewhat similar, but I did have the experience with the Rust. And so that was kind of a good kind of complemented each other. It's like, okay, I see kind of like maybe what like Adrian Sabolt's doing with NumPy and Rust. Maybe we can kind of share some of the code that's he's been doing and then use that within PyMC BART to help kind of at least with the log probability evaluations and so forth. And so, yeah, this really stemmed from Osvaldo wanting to make it more performant, and then me stepping on board and saying, "Hey, okay, let's implement this in Rust, and then share some of the code base from Pi."
Okay, okay. And so how was the experience? Like it was Rust all new to you? How do you even start on such a huge project?
Yeah, so I do have prior experience with Rust within some data processing pipelines in the IoT lab. So the Rust part wasn't entirely new to me. But what was new was kind of interoperating with Python, having Python bindings. So that way the Python user, when they call the BART code, it executes the Rust implementation. But in regards to the implementation process, essentially the approach I kind of took was, okay, let's implement this kind of essentially one for one from the Python implementation into the Rust implementation. And then from there, we can start to kind of optimize whether the different functions or methods. And then that way we can get a more of a nice performance improvement instead of kind of just immediately rewriting something. Then we wouldn't know maybe like, okay, now this isn't kind of working right. Where did that go wrong and so forth. And yeah, I don't know if you want to talk about some of like the Rust specifics or the algorithm specifics or.
Yeah, maybe so. It's been a while since we talked about BART and regression trees on the show. So maybe if you can introduce the methods, the tree methods in general. You mentioned gradient boosting. We obviously mentioned BART. So maybe give us just the elevator pitch for BART and tree methods in general. And then I think it will be useful to dive into a bit more of the technical details of the algorithm to understand really how the methods work and why people could be interested in using BART and in which cases.
Yeah, so yeah, at a high level, then like you have these tree-based methods, and at like the simplest level, you have your decision tree, and so that's kind of just your logic. Like if this variable is greater than some value, you kind of go down the tree, and then you finally get to a leaf node, and that's kind of like your prediction for a target or your response variable. So building up off of the decision tree, you can have like a random forest, which is then like a bunch of those decision trees together into a forest. Um, but then kind of even stepping up on top of that, you have like boosting methods. And so this these methods are really where you attempt to like learn, like you use kind of like the random forest, but you learn like the residual between the tree, the difference in the tree's predictions. And so when you start to do that, you're kind of like it's kind of like a meta learner. You're kind of learning where each tree is doing bad at to kind of come up with a better producing or better predicting tree. And so this is kind of really more where BART is aligned with the gradient boosted methods rather than a random forest, because BART is kind of doing the same thing as boosting these gradient boosted methods. The way it's kind of assembling these trees is different. Um, and the way that the BART assembles these trees is by taking random perturbations and then assessing the log likelihood of that tree.
Okay, yeah. Yes, that's closer to gradient boosting way of doing things, right? Yeah. And okay, so that's the elevator pitch. Now, when are these models particularly useful in your experience, and what is their strength and drawbacks?
So one of the strengths I think like if you want to kind of compare like BART and like a traditional maybe XGBoost or light GBM model, one of the big benefits of BART is that you get the uncertainty quantification. You have a posterior over decision trees. And so then with that, you can actually stick that model into maybe other things that you want to use uncertainty for. For example, like Bayesian optimization traditionally uses Gaussian processes, but you can actually stick this BART model into the Bayesian optimization routine as well, because you also have the uncertainty there. But one of the big drawbacks with BART is that it's famously slow compared to the like XGBoost or like GBM. And so that's kind of one of the big drawbacks I see there with that method. But another nice thing about BART is that uh, so with like XGBoost and like GBM, it's very easy to overfit on your data. And so you need to look at a lot of like loss curves and figure out, okay, hey, when do I stop training? How many trees do I use? How many learners and so forth to kind of stop the tree from training and stop the tree from overfitting. But with BART, it's really nice because we have regularizing techniques. So that way we avoid overfitting kind of inherently within the method. And so that's one really nice kind of pro I see with BART over the others. But yeah, the big, I'd say, con is that it's significantly slower than the other ones. And that's just for multiple reasons.
So yeah, thanks a lot. This is much clearer. So, and I hope it is too for listeners. So now I think it's a good time to dive into why that would be, like, where the bottlenecks are and why, like, what's the algorithm per se and how does it work basically under the hood so that people really understand the models when they use that.
Yep. So in regards to like PyMC BART, we implement, as I think we stated before, particle Gibbs, whereas other implementations might implement like a Metropolis Hastings approach. And so with the particle Gibbs step, how the algorithm works is that so we generate a set of trees, so maybe 50, or in PyMC BART, you define the number of trees and the number of particles. And so, for example, you might say, okay, we want 50 trees and then 10 particles. And so now we're gonna perform a series of particle Gibbs steps. And so at the first step, we're gonna loop through all 50 trees. So for the first tree, we're gonna initialize then maybe 10 particles, whatever you define. And then for all those 10 particles, which are just decision trees, we perturb each one. Maybe we sample for a variable, a certain split value, and then another split value, and then we assess the log likelihood. And then at the end, we say, okay, hey, this particle, maybe particle 5 out of the 10, that's going to replace the current tree, which is 1. And then we proceed to the next tree. Tree number 2, we go through that same process, initialize 10 particles, perturb each one, weight them according to the log likelihood, and then replace that tree. And we continue until all 50 trees are essentially replaced. And so, yeah, that's really kind of at a high level, the algorithmic steps. It's really quite a simple process, which is quite surprising if you read kind of a lot of these papers.
Yeah, and were you already versed that much into BART and tree methods before working on that, or did you get that knowledge by working on this project?
Not really. So it was mainly knowledge from working on the project and
Mm.
reading the code base that Osvaldo and others did, which was
Mhm.
quite readable, which is really nice. Nice procedural kind of line by line. Oh, this is what it's doing.
Yeah.
And so that really kind of helped with the intuitive understanding of, oh, hey, this is what the particle Gibbs is doing. This is kind of, yeah.
Hmm. Yeah, yeah. And I second that. Yeah, the code base is really well done and written, and it's quite easy to start contributing to the package. So
Hmm.
this is really awesome because I've dabbled a bit with BART for work in baseball, and
Hmm.
I haven't tried yet your Rust implementation because that is very useful in baseball because there is a lot of use cases for methods like BART, but there is so much data that you often need an acceleration somewhere. So yeah, whether it's using classic PIMC BART on a GPU or actually using your Rust implementation and adding a GPU on top of that, that should
Hmm.
probably be a really good boost to sampling speed.
Yeah. Yeah. And I must say one of the things that's really nice with PyMC BART is that there's several things like really nice enhancements that we have. And so if you go look around online, a lot of the other packages are specifically for Gaussian likelihoods. So that's the first one. So you can't really model like a Poisson process or any other. The second one is that we also offer various split rules. So if you have in your design matrix numerical features and categorical features, you can pass split rules specific for that data type. And this is something that's common in other packages that it kind of just assumes everything is a numerical value. And so that those are kind of the two really nice things that I think differentiates kind of our package. But then lastly is that like we have the BART kind of random variable and how this is embedded in PyMC, and so
Right.
you can model the linear predictor, you can model the sigma, that parameter, and so that's really
Yeah.
nice because you can build essentially arbitrary probabilistic programs with BART,
Right.
whereas other package it's kind of that's
Yeah.
you use that method and that is the method that
Yeah.
you use.
Yeah. Yeah, exactly. This is actually a very good point. Yeah. That you can add that as a module in a Painter model. So you could model your linear predictor with a classic linear regression, and then your sigma, your standard deviation, you could model that with a bot,
Yeah.
a random variable. So this is very useful. And
And yeah,
yeah,
and I must say that recently in the current existing Python implementation, support has been added for more than one BART random variable,
yes,
which is really great and has been
yeah,
something that's been requested.
yeah. So you could do two different bots on two different parameters. So this is really awesome. In a way, that's starting to look a lot like the GP submodule. Right? GPs, you
Hmm.
can add them to PIMC models really as you want. And you can have different GPs for any number of parameters you want in your model. And you really cannot do that with like GP packages, GP focused packages.
Hmm.
Most of GP focused packages is, well, you can just use GPs. That's all.
Hmm.
You cannot do anything else. And often also likelihood limits. In PIMC, you can use a GP with any likelihood distribution. In most of the packages, it's often normal likelihood because that's
Yep.
often how it goes. Yeah. How is it? So I know on the BART, pure Python BART, we can use any likelihood we want. How is it on the Rust side now? Because I remember at the very beginning, you had not included yet categorical multinomial ability to use that kind of likelihood. And of course, I always use that likelihood. So I was like, ah, damn, cannot use that yet. But yeah, how is it right now when it comes to the likelihood, and especially the most multidimensional one, which I know much more of a pain to develop.
Hmm. Yeah. So in regards to the current state of the Rust implementation, there are still some things that are implemented one-to-one, and I'm still working on that. But in regards to the likelihood, that's been resolved. So you can model multiple different likelihoods. But I think the one you were specifically asking was in regards to the different split rules, like the categorical and like continuous split rules. And that is also now implemented in the Rust implementation. But the one thing that's not yet is the multiple BART random variables. I still am working out some bugs there.
Yeah.
And so that's still something that's kind of being implemented on our end.
Okay. Yeah. So concretely, we can do anything with BART Rest that we can do with BART, except for having more than one random variable, BART random variable in the BART.
Yeah.
Otherwise, everything is on par right now.
Yeah.
Amazing. Yeah, it is cool. Yeah. Thanks, Gabriel.
Yeah,
It's really awesome. That means now we'll be able to use that much more on baseball data. This is going to be super fun. And how do you squeeze that in? Actually, like, is it part of your job, or is it something you do on the side? And like, maybe you have some advice for people who want to start doing some open source like we do, and they want to have some practical advice of how to squeeze that in the work and their free time, because in the end, this is really what research is about, right? Trying to push the envelope on very frontier topics, which are not only going to pay off for your project, but for your company as a whole and a lot of other people who are going to use that afterwards.
Yeah. And so, luckily with this kind of, a lot of the stuff I do at work uses these tools. And so if like our team and me see kind of like, hey, it would be really nice if we could speed up BART because it would help our problem at work. And then like doing the open source at work kind of aligns quite nicely. But if the problems aren't really related, that's kind of in my own time and so forth. But in regards to contributing more generally, I honestly, the PyMC and Bambi community is just, I think, one of the best in the scientific open source community. Everyone is very inviting and willing to help. But my advice I'd say to people starting out is don't bite off more than you can chew. Pick kind of maybe the low hanging fruit and then work your way up from there. I've found to be quite a fairly more safe approach, and kind of goes better with the maintainers that way.
Yeah.
Let me show you how to be a good Bayesian.